Welcome to the Space Telescope Public Lecture Series. Tonight's topic, Surprising Supercharged Science with Swift. And our speaker is Steve Kerby from Penn State University. I am Dr. Frank Summers of the Space Telescope Science Institute. My pleasure to be your host here tonight and every month. And I always want to thank our amazing tech team, Thomas Marufu and Grant Justice. However, we have a special guest person because Thomas was unable to make it tonight. So Gary Gilbert, I want to thank Gary for stepping in at the last minute. I will also remind you that the Space Telescope Public Lecture Series will continue to be online only throughout 2023. In 2023, we will have our talks starting on January 17th. Now, the first Tuesday of the month is January 3rd, but I will actually be out of the country on January 3rd. And on January 10th, we have the American Astronomical Society meeting, so we will not have a talk until January 17th. And as you can see, I do not have a person slated in for that talk right now. I have worked on it, but I have not been successful at getting somebody to commit. But I will, as you know, I get someone every single month. So in January, it will be a fascinating topic by an insightful speaker on January 17th. In February, Darshan Kakat has volunteered to give the talk. However, he did not give me a topic. So it will be an insightful topic on February 7th. On March 7th, Travis Fisher will be giving the talk, and he will be speaking about active galaxies. When that information is finalized, it will appear on our website, www.stsci.edu/public-lectures. And this is the web page. On the left side, you have the links to our webcast, both on YouTube and on the STSCI webcasting. And on the right, you can see the email sign up. Just put your email address in there and you will get 1 or 2 emails a month telling you about our lectures. Also on our website, we have the links to the upcoming lectures. And for each lecture, we have the speaker, the description of it, and after it has been recorded, links to the STSCI webcast and the YouTube webcast. In terms of email, for announcements, easiest thing to do is sign up at our website, as I showed you. You can also subscribe to our YouTube channel, youtube.com/Hubble Space Telescope, all one word. When you subscribe, you will get notices of new videos and reminders of live events such as this. Further, if you have comments or questions after the event, you can send them to publiclecture@stsci.edu. In terms of social media, we do the social media for the Hubble Space Telescope, for the Webb Space Telescope, and for the Space Telescope Science Institute on Facebook, Twitter, YouTube, and Instagram. I myself send out a couple things a month on Facebook and Twitter, and actually they're mostly about the public lecture series. So you're not going to get a ton of original content if you follow me on those. And now, the news from the universe for December 2022. Our first story for you tonight. A distant supernova 3 times over. This is a really cool story, but you got to think through it. So put on your thinking caps here, right? We're going to start with this cluster of galaxies. This is the galaxy cluster called Abell 370. And Abell 370 is one of these really, really, really massive clusters of galaxies. It's so massive that the mass of it warps space. Via general relativity, mass warps space. And the mass inside this galaxy cluster warps the space, and so you get what's called gravitational lensing. The light passing through this cluster actually travels in many different pathways. It gets warped as it goes through. And in particular, we're going to pay attention to this galaxy up here in the upper left. I don't know if this galaxy has a name, but this is the focus galaxy for tonight's story. And there has been, is part of it is involved in the gravitational lensing. And what you see here is that there is these 1, 2, 3 different images of a background galaxy. So the light from a background galaxy has traveled 3 pathways around this galaxy, and we see 3 images of that galaxy. That's one of the cool things about gravitational lensing, is that the light can travel multiple pathways through a cluster like this, and you can see the same object 3 times. Now, what's even cooler about this is that back in 2010, in December 2010, there was a supernova in this lensed galaxy. Okay, so this background galaxy that's going through, and you can see the galaxy 3 times. And if you look really, really closely at this one, you can actually see that there's an extra bright spot. That's a supernova. Now, if you just want to see only the supernova, what you can do is you can take that A image and subtract it from the B image, and you get rid of all the normal stuff, and you're going to leave just the supernova. All right, and so here is this, what we call the difference image. All right, image B minus image A, and you can see you get rid of that big galaxy in the cluster, you get rid of the galaxy that's actually being lensed, and all you're left with is the supernova. All right, and so you've got 3 images of this supernova in a very, very distant galaxy. Finally, here's the kicker, right? That the light paths that go through the cluster are of different lengths. Therefore, it takes a different amount of time for that 1 image, or that 2 image, or that 3 image to pass through the cluster. So you're actually seeing the supernova at 3 different times, okay? And if we take not just 1 wavelength, this is a black and white here from just 1 wavelength, but if we take 3 or 4 wavelengths, I guess it's 3 wavelengths, then we can make a color image of this difference image. So here is that color difference image, and we've marked it with the amount of time that it takes, that the time difference. So image 1 is the first one to arrive to us, call that day 0. Image 2 arrives 2 days later, and image 3 arrives 8 days after the first. And what you're seeing here is actually a color change, that the supernova is evolving. It's changing its color over the days. Now, we're not taking images on different days. We're taking 1 image, and that 1 image is showing you 3 different times in the supernova. So we're looking at this huge galaxy cluster with thousands of galaxies. And then we look at this 1 galaxy where there are 3 images of this lens galaxy. And within that lens galaxy, we're seeing a supernova. And we're seeing that supernova at 3 different times. And we're seeing it evolve over the course of a week. That's a cool observation. And it gives us a lot of science about what's going on in this supernova explosion that takes place on the other side of the universe. Our second story tonight, a young star spews forth. This is a gorgeous new image from the Webb Space Telescope. I mean, just look at that. That's beautiful. But what is it? Well, if you don't read the words on screen and you just look at the image, you might say, wow, that looks like it's a planetary nebula, because we've got this wonderful image from Hubble of the Butterfly Nebula, and it has that same sort of bow tie shape or butterfly shape, but it's not. Okay, it's not a planetary nebula, because a planetary nebula is the death of a star, whereas the one on the left from Webb is actually a star that's just been born. Okay, so although it looks like the death of a star, it's not the death of a star. This is a protostar, a star that's just in the process of forming. And you may ask, well, how can we tell? Well, if you look at this part right in the center, you can see a dark dust lane right here in the center of the object. This is a dusk disk, and astronomers have measured that, and actually found it's got Keplerian rotation, just like a forming solar system. All right, just like the solar system, it has the rotation characteristic of a solar system. And if you look at the emission in various bands of infrared from various satellites, it has the characteristics of a really, really early solar system. We're talking a solar system that's 100,000, 200,000 years old. Now, I know, 100,000 years old, that's really old for you and me. But, stars, our sun is 5 billion years old. So something that's few 100,000 years old, that's like just been born. This is just been born. And it's obvious if you look at a different part of this image, right? And here in the northern lobe, you can see all these bubbly things, right? Well, this early stages of this star formation of this star is obviously given to lots and lots of eruptions. So what's going on here, what you're seeing in this thing, is you got the disk of material, and material is falling onto the star. The star is still forming, material is still forming. So from the plane of the disk, material is falling on, but then material is being spewed out perpendicular to that, okay? So at the poles of the disk, the material's being spewed out, and you can see how far out into space it gets thrown. It gets thrown many solar systems out into space, and you can see that these eruptions are not. It's not like a single eruption. It's not like one continuous spew of material. It's actually multiple eruptions and things spewing material out as a star formed. And it shows you that although I often think of stellar death as some of the most beautiful images in astronomy, you can get some really great ones with these protostars, especially when you look in the infrared with Webb. All right, and we have a bonus story for you tonight because the Pillars of Creation is up for its encore. If you are here last month, I talked about the pillars in the Eagle Nebula from Webb, and I showed you also the Hubble ones, the precursor to it, and the near-infrared and the mid-infrared image were where I ended last time. However, there was a presentation at NASA headquarters just a few days ago for the French President Macron, and for that, we combined the near-infrared and the mid-infrared into a single image. And here it is. This is just recently released from Webb. Both the Pillars of Creation in near infrared and mid infrared combined. So let me go back to here. They are separate, and here they are combined. And it shows you how you can look at it in different band passes, combine the band passes, and you really get beautiful, beautiful images no matter what here. All right. So that is our news, and I gotta figure out, how do I stop my screen share? There I do. Okay, we're using some slightly different software tonight. So our speaker tonight is Steve Kerby from Penn State University. And usually I give you the pedigree about where they got their PhD and where they did their postdocs and where they've done their jobs, but Steve is special here. He is still in his graduate work, working on his PhD at Penn State. He did his undergraduate work at Case Western Reserve University in physics and astronomy, and is now is now at Penn State, as I said. He tells me he hails from Wheaton, Illinois, which all astronomy buffs know is the home of Edwin Hubble. So he's got quite the pedigree to live up to in his hometown. He tells me that when he is not doing astronomy, he's either playing the electric bass or the harmonica doing music, or he's often involved in theater, something that occupied me a lot when I was younger, not so much anymore. So Steve, why don't you start your screen share? And ladies and gentlemen, Steve Kerby.
Thank you very much for the introduction. Let me just share my screen here. Can you see my presentation okay?
Yes, we can.
Excellent. Once again, thanks for the introduction. My name is Steve Kerby. Like Frank said, I'm a grad student at Penn State University, currently pursuing a PhD in astronomy and astrophysics. And today I'd like to tell you about my favorite space telescope, all due respect to Hubble and JWST, the telescope that I use my science for, and its 18-year history of making fantastic discoveries all around the universe. And that's the Swift Observatory. So buckle up for what I hope is some exciting new science, and we're all going to learn something new tonight. Oops. There we go. Swift was actually in the news recently. Just about a month and a half ago, Swift and another high-energy space telescope, the Fermi Space Telescope, made headlines that were picked up by major news organizations for the discovery of a gamma-ray burst. LeBron James, I went to undergrad in Cleveland, LeBron James might be the greatest of all time, but this gamma-ray burst was quickly termed the brightest of all time, or the BOAT. Swift was instrumental in making this discovery, and this is just one of the most recent in a long history of famous discoveries, new finds, and fantastic science that Swift has done. While Swift is a slightly smaller observatory, slightly more low-key than famous missions like Hubble and now the James Webb Space Telescope, I like to think of Swift as the most amazing space telescope that most members of the public have never heard about. So tonight, I'm going to talk a little bit about Swift, its history, its unique design that makes it such a fascinating tool for astronomy, and finally about the discoveries it's made over its history, and how I use it to investigate supermassive black holes in the distant universe. So without further ado, let me introduce the Swift Observatory, formerly the Neil Gehrels Swift Observatory. It was renamed a few years ago after the original PI of the mission, Neil Gehrels, who was a pioneer of gamma-ray astronomy. Sadly, he passed away a few years ago. Now, obviously, you can make out one of the most important features of Swift immediately, and that's Swift is a space observatory, just like Hubble and James Webb Space Telescope. Part of the reason Swift is a space observatory is that the science that Swift wants to do can only really be achieved from orbit, above the Earth's atmosphere. We're going to talk about the unique scientific goals and techniques that Swift pursues in the first part of this talk. Just like many other space telescopes, you can see several common features that Swift shares. It's got solar panels for collecting power, a satellite bus at the back of the telescope for holding computers and detectors, and finally a few telescopes at the front. We'll talk about those again in a little detail in the future. So, Swift, a space telescope just like Hubble and JWST, but it's got some unique features that make it good for a special, unique types of science. Before we jump into the nitty-gritty details, I'm going to give a super brief overview of Swift's history up in space. Swift just actually very recently turned 18 years old, which means it's old enough to vote officially. Swift was launched on a Delta II rocket in 2004, so it's been in orbit above the Earth for the past 18 years. Obviously, space telescopes take a while to design and build. Swift was in conception, construction, and testing before its launch, just like Hubble and JWST. Well, after it launched in 2004, it immediately set about making fantastic scientific discoveries, detecting its first gamma-ray bursts in 2004 and 2005. We'll talk about what a gamma-ray burst is later in this talk. It's not all been smooth sailing for Swift, though. Only less than a year after it's launched, the X-ray telescope aboard Swift was hit by a micrometeorite, a small piece of space debris. And as you can see in the picture here, that really messed up the telescope, that we have to account for that over the past 18 years. Earlier this year as well, Swift had another little bump in the road when its reaction wheels, part of the telescope that help aim it around the sky, one of them malfunctioned, and Swift had to be shut down for a few months as engineers found a solution and got it back on its feet. Swift is still going strong today. I depend on its observations for my own research. But at 18 years old, it's starting to show its age a little bit. I'm confident, though, that Swift has another decade in it, or even more, and I hope to continue doing science on it as I pursue my PhD and beyond. So, let's just jump into the nitty-gritty details then. This talk is organized into three broad sections. First, we're going to talk about how the Swift Observatory works, what makes it special, and why was it designed in such a unique and fascinating way. Next, we're going to talk about some of the most famous discoveries that Swift has made, both gamma-ray bursts and other objects. Obviously, this isn't an exhaustive list. This talk would take hours and hours if I had to talk about every amazing discovery Swift made in the past 18 years. These will just be my personal favorites. And finally, for the third and final part of the talk, I'll talk about my own research involving Swift, how I investigate distant active galactic nuclei, supermassive black holes, using Swift's unique capabilities. So, to start off with, let's talk about how Swift works, and why it's designed that way to do its fascinating science. We'll start with a little bit of background information. Let's talk about the electromagnetic spectrum of light. About 200 years ago, scientists around the world started discovering that there are types of light beyond the rainbow, red, orange, yellow, green, blue, and purple, that we humans can observe. First, they discovered infrared and ultraviolet light, and then, over the next 100 or so years, extending the electromagnetic spectrum to a huge continuum of different types of light. If you look on this plot, we humans can only observe light in this little red block here, what we call visible or optical light. Photons of that energy of light strike our eyes, and we observe them as red, yellow, blue, etc., different colors. However, as it's clear on this slide, there are huge varieties of photons beyond that limited optical range. Humans are truly limited to just a tiny sliver of the total band of different types of photons. From the gamma rays at extremely high energy on the right, to the X-rays and ultraviolet light, and then in the low energy side in infrared, where the James Webb Space Telescope observes, the microwaves and radio waves, astronomy uses every different type of photons in a complementary way. Using different types of photons is called multi-wavelength astronomy, and Swift is a powerful tool for doing multi-wavelength astronomy, because unlike humans, Swift can observe a wide variety of photons across the spectrum. Humans are limited to this little red block in the center of the screen, the optical or visible light, but Swift can observe visible light, ultraviolet light, and two different types of X-rays, all the way up to light that's over 100,000 times more energetic than the light that we see with our own eyes. So, in this way, Swift is a powerful telescope for conducting multi-wavelength astronomy. While telescopes like Hubble and JWST observe in the optical or infrared bands, Swift observes in the optical, ultraviolet, and X-ray varieties of light, making it extremely versatile and a very flexible instrument. We're going to talk a little bit more in the next few slides about why it's so important that Swift observes this wide band of the electromagnetic spectrum. Another factor that's important to keep in mind as we talk about Swift and its design, that there are really two types of objects in the sky. One of them, the one we're most familiar with, astronomers call steady sources. These are astronomical objects that shine for millions or billions of years uninterrupted. On the right side of this screen, you can see two different images of the Pleiades, which is a group of young blue stars not too distant from here. On the upper right, you can see the Pleiades as they were observed by Galileo, an Italian astronomer 400 years ago. And on the lower right is a picture of the Pleiades taken by a modern space telescope. You can see that the same stars are visible in both images, in approximately the same locations as well. The Pleiades, many of the stars we see in the sky, and many astronomical objects are steady sources. They last for millions or billions of years with only small changes in their brightness. Other objects, though, are what astronomers call transient. That's just a fancy term for something that lasts only a short time in the sky before fading away. The supernova that Frank mentioned in the newscast are one such transient. These are exploding, dying stars that shine brightly, outshining their entire galaxy for only a few days or weeks perhaps before fading away into nothing. Obviously, transients are exciting laboratories for doing high-energy astronomy. The procedures that can release a galaxy's worth of energy in just a few days certainly are at the very cutting edge of high-energy physics. But because they don't last for millions of billions of years and often never repeat, it's very difficult to observe transients with astronomical telescopes. As soon as you look in their direction, they might have been gone already. Swift tackles this problem as well. And we're going to talk about why Swift's unique design makes it so effective both at observing transients and at steady sources in the context of its original mission, observing gamma-ray bursts. Gamma-ray bursts are a particularly spectacular type of astronomical explosion. Gamma rays, remember, are the highest energy type of photons in the electromagnetic spectrum. They have at least 1,000,000 times more energy than the photons that we see as optical or visible light. And a gamma ray burst is a blast of these high energy photons emerging from deep space. It only lasts seconds or minutes, and then it fades away forever. You can see on the plot on the right here a typical gamma ray burst, how the number of photons arriving in a detector suddenly leaps up to thousands of photons per second, and then within 60 seconds has faded away forever, never to return. Incidentally, the history of gamma ray bursts is a particularly fascinating topic. They were discovered in the 1960s by Cold War nuclear spy satellites. The various nuclear powers were putting up gamma ray detectors in space, hoping to find their Cold War antagonists conducting nuclear tests. But instead of detecting hundreds of nuclear explosions on Earth, fortunately, these Cold War satellites also detected hundreds of gamma ray bursts coming from deep space. This launched another important side of astronomical observations, as scientists worked for decades to try and figure out exactly what makes gamma ray bursts so unique and special. Again, what's the challenge of observing gamma ray bursts, though? And why is Swift, a telescope launched only 18 years ago, one of the most powerful instruments for solving this decades-old problem? And that's because of a big difference between Swift and other astronomical observatories. I've made a little cartoon on the right here about how a typical proposal process happens for a famous telescope like JWST or Hubble, or even famous ground-based telescopes. First, the telescope operators, like the Space Telescope Science Institute, or NASA, who run various other telescopes, solicit proposals from astronomers. Astronomers write proposals detailing in depth the very exquisite reasonings why their suggested observations are the most valuable that could happen. These take the form of 20, 30, 40-page long papers over a period of months and months. After a review process, people who operate individual telescopes select certain observations, and then the telescopes go about the sky, pointing at different objects, observing them for extended periods of time. The problem, though, is that gamma ray bursts flash and emit copious amounts of gamma rays for only a few minutes, and then disappear and never appear again. If it took months and months and months to aim a telescope at a gamma ray burst, the gamma ray burst would probably be gone by the time you found it. Swift was designed to tackle this problem with a powerful combination of automatic rapid response and multi-wavelength observations. So let's dive into the details of what makes Swift's design so powerful for observing these strange, exotic, extragalactic gamma ray bursts. The first tool that makes Swift powerful for tackling these gamma ray bursts is that Swift is fast. We all know that astronomers love making weird acronyms up for their telescopes, but the Swift in the Neil Gehrels Swift Observatory isn't an acronym. It just means Swift is fast. Swift can point itself anywhere on the sky within 90 seconds. So Swift can point due east and then turn all the way around to due west in just over a minute. And it does this using reaction wheels. Think of a reaction wheel as a gyroscope, a way to use conservation of momentum to turn yourself around when you can't push against the air or the ground like a normal telescope. By comparison, it takes the Hubble Space Telescope up to 30 minutes to point up to a location on the sky. Hubble's an extremely powerful telescope, but Swift, with its compact frame and 6 powerful reaction wheels, can rapidly turn itself anywhere on the sky. Obviously, for observing something like a gamma ray burst that lasts only minutes before fading away entirely, this is an extremely valuable capability. Swift can follow up at a gamma ray burst with such rapidity and observe it before the burst fades away. If you didn't have this capability, you'd just have to look at a part of the sky and hope a burst occurred while you were looking at it. But with Swift, you can follow up instantaneously within 90 seconds. Swift has another capability that makes it very powerful for following up gamma ray bursts, and also for conducting a wide variety of other science. And that's Swift actually has 3 eyes. It's a 3-in-1 telescope deal. Get it while it lasts. That's right. Instead of just one telescope, the Swift Observatory is actually 3 telescopes. Those are the burst area telescope, the X-ray telescope, and the UV optical telescope. We're going to talk about each of these in turn. Each does slightly different things. Each serves a different purpose in exploring gamma ray bursts, and each has different capabilities for doing multi-wavelength astronomy. That's one important thing to keep in mind when talking about Swift. It's 3 telescopes in a single observatory, all on one satellite. And that's the real heart of why Swift is such a powerful tool for astronomy, even 18 years down the line. So let's talk about each of these telescopes in turn. What do they contribute to the mission of detecting and exploring gamma ray bursts? We're going to start with the first of these 3, the Burst Area Telescope. I like to think of the Burst Area Telescope as the Where's Waldo telescope aboard the Swift Observatory. Its primary goal is monitoring the sky and detecting a burst of high-energy X-rays, finding those gamma ray bursts or cosmic explosions that last only a minute or so. The Burst Area Telescope, or BAT, detects X-rays between 15 and 150 kilo-electron volts. A kilo-electron volt is a unit of energy. An electron volt, 1,000 times smaller, is about the energy of a photon that we observe with our eyes. So the Swift Burst Area Telescope observes photons that are between 15 and 150,000 times more energetic than the photons that we observe with our eyes. Using the Burst Area Telescope, Swift automatically detects and locates gamma ray bursts or other high-energy explosions to within half a degree on the sky. For context, if you were to go outside right now, and if it's clear where you are, the moon, which is about full today, is about half a degree on the sky as well. So the Swift Burst Area Telescope can locate cosmic explosions to within about the area of the moon on the sky. It's also important to remember one of the primary reasons why Swift is a space observatory, and that's because high-energy photons like X-rays or UV photons cannot pierce through the Earth's atmosphere. Photons as energetic as 1, 10, or 100 kilo-electron volts, that's over 1,000 times more energetic than our own eyes, can't get through the thick layer of gas that envelops our planet. If you were to take Swift and put it in your backyard, pointing it up at the sky, please don't do that. A lot of people who are trying to operate that telescope would be quite alarmed. If you were to point it up at the sky in your backyard, the X-ray telescopes would not detect anything coming from space, because the X-rays can't pierce through the Earth's atmosphere. The Swift Burst Area Telescope isn't like most telescopes you're probably familiar with mirrors and lenses to focus light down onto a detector. The Swift Burst Area Telescope uses what's called a coated aperture mask, which you can see on the drawing to the right here is a complex pattern of opaque and transparent material. It looks a little bit like static on an old television screen. The dark and light patterns mean that when high-energy photons arrive at the Burst Area Telescope, they create a pattern of light and darkness, illuminated and dark parts, on the detector array below. That's that yellow rectangle you see sitting below the coated aperture mask above it. Think of it like this. Imagine you have a fence with slats in it, a slatted fence with vertical slats. As a car drives by, a pattern of light turns through those slats, and using the different angles of the light coming through those slats, you can estimate where the car is. In a similar way, when a gamma ray burst occurs somewhere on the sky and the photons hit the coated aperture mask, Swift uses the pattern of light and dark on the detector from these strange random light and dark, opaque and transparent materials to find out exactly where that burst of photons came from on the sky, to within half a degree. This is the first step of examining a gamma ray burst with Swift. Burst Area Telescope finds the location of the cosmic explosion to within about half a degree. While Swift is looking around the sky for gamma ray bursts or other high-energy explosions, it's not just sitting there letting all the data go in the bin. Swift is taking observation not only from scientists who would like to use its telescopes to do individual astronomy projects, but also the Burst Area Telescope builds up a list of steady sources. These sources might be very dim. They might only have a couple photons trickling in per second while the Burst Area Telescopes look at them. But with 18 years of continuous sky monitoring, the burst area telescope can build a map of the high-energy sky, which you see on the lower left here. However, when a bunch of high-energy X-rays arrive all at once, Swift's automated computerized process realizes a gamma-ray burst has arrived, or another cosmic explosion has occurred, and the entire telescope suddenly springs into action, turning around with its powerful reaction wheels and trying to seek out that gamma-ray burst. We're going to come across this theme a couple times as we continue to talk about Swift. Swift's mission, observing gamma-ray bursts, is an automated process, but in its downtime, when Swift isn't pursuing a gamma-ray burst, it's doing valuable science on the side. We're going to come back to that again a little bit in the future, but let's pick up with the gamma-ray burst we just detected. The burst area telescope has located a gamma-ray burst on the sky to within half a degree. As the telescope swivels to point at this region of the sky, the second of Swift's 3 telescopes springs into action, the X-ray telescope, or XRT. The Swift X-ray telescope observes photons that have between 0.3 and 10 kiloelectron volts of energy. These are called low-energy X-rays, in contrast with the high-energy X-rays observed by the burst area telescope. These low-energy X-rays are observed with Swift's X-ray telescope. You can see the telescope before it was installed on the observatory in the lower right side of this screen. On the upper right, you can see a typical gamma-ray burst observation from Swift. After the burst area telescope has given us a half-degree region on the sky where the gamma-ray burst might have come from, the X-ray telescope looks in that same region of the sky and tries to find an intense bright source of X-rays that wasn't there previously. You can see here that the red and blue circles are where the burst area telescope indicates that the gamma-ray burst might have come from. And in the green circle, Swift has detected an intense source of low-energy X-rays. That means Swift has pinpointed exactly where on the sky the gamma-ray burst came from, to within 5 arc minutes. An arc minute is a unit of length on the sky that astronomers use. That's about a factor of 2,000 smaller than the half a degree precision of the burst area telescope. So, the Swift X-ray telescope complements the burst area telescope by picking out the intense bright source of X-rays that's flaring up as a cosmic explosion occurs. Just like the burst area telescope, though, in its free time, Swift is pursuing astronomy around the sky. I use the X-ray telescope to observe distant galaxies across the universe because it's a powerful X-ray telescope, similar to these mysterious high-energy cosmic explosions. It's chasing down fascinating science from astronomers around the world. I'm going to take a step back, though, and talk about a pesky micrometeorite that I alluded to earlier in the talk. Micrometeorites are tiny little fragments of rock and dirt. They're moving at about 20,000 miles per hour past the Earth. And while they burn up in the atmosphere and so are pretty harmless to people here on Earth, they can be quite hazardous to space observatories or other satellites above the atmosphere. Like I mentioned at the beginning of the talk, Swift got unlucky, and its X-ray telescope, its second telescope, was hit by a micrometeorite under a year into the mission. You can see on the right side of the screen here in the upper right an observation of a bright X-ray source after the micrometeorite struck it in 2005. And you can see several columns of the detector have been damaged or put completely out of commission by the impact. Think of it like if you have a liquid crystal display on your computer and an impact causes a region of that display to become dead. You need repairs, but unfortunately, Swift's orbiting above the atmosphere, so we haven't got around to replacing the detector. This might seem like extremely bad luck, and sure enough, it was quite unfortunate that this happened so early in Swift's mission. But I'm sure folks who are well-versed in the James Webb Space Telescope know that micrometeorite impacts they happen. It's just bad luck when you're doing space astronomy. On the lower right side of this screen, you can see the mirror alignments of the James Webb Space Telescope before launch, and then after a pesky micrometeorite of its own struck one of the mirrors, causing a little defect. Swift, just like the James Webb Space Telescope, though, is still going strong after these impacts. Telescopes can continue to take observations even with these little defects. But that's just something to keep in mind when doing observations with space telescopes. Every time I analyze Swift data, I need to run it through a computer program to account for these defects. Hopefully it doesn't get hit by anything again, let alone anything bigger in the next few years. Let's talk about X-ray telescopes, though, for a little bit. This will help give us context when I show you pictures of what a Swift observation through XRT looks like. X-ray telescopes, just like the burst area telescope, aren't really similar to the telescopes you might have in your backyard or that you see in domes on top astronomy observatories or astronomy buildings at universities. Because X-rays are so energetic, with thousands or tens of thousands of times as much energy as photons we humans observe, they only reflect off mirrors or reflective surfaces when they arrive at very low angles. I like to think of this like trying to skip a stone across a smooth lake. If you drop the stone in vertically, it'll just sploosh, go into the water. It won't skip at all. But if you skip the stone with a very low angle at high speed, it'll bounce off the lake several times. Similarly, X-ray telescopes use very gently curved mirrors that kind of funnel the photons down onto a detector. If you look in the upper left side of this slide, you can see X-rays coming from the right, bouncing off a series of geometrically shaped mirrors and being focused down onto a detector. Put together, an X-ray telescope looks something like on the lower left, a giant cylinder of these metallic surfaces gently focusing X-rays down onto a detector plane. That's very different from the mirrors or lenses that we're familiar with when you see when you use a backyard telescope, for example. That'll help us give some context when we compare the XRT and UVOT telescopes of Swift. So, the Swift Observatory detects a gamma ray burst with the burst area telescope. It uses the XRT, the X-ray telescope, to find the precise location of the gamma ray burst to within a few arc seconds. And finally, the third telescope aboard Swift kicks into action. The UV optical telescope observes optical or visible photons and near ultraviolet photons. The optical and visible photons are the ones that we see with our own eyes, and the near UV photons are just more energetic than the blue or violet side of the rainbow. The UVOT, the UV and optical telescope, looks very similar to most telescopes we're familiar with. It has a similar design to Hubble or a backyard telescope you might use for your own observations, with mirrors and lenses focusing light coming from deep space down onto a detector plane. Remember, after detecting a gamma ray burst, Swift has automatically turned towards the region of the sky where it came from, and the XRT has located the precise location of the gamma ray burst. The UV and optical telescope watches the gamma ray burst fade away gently. As the gamma ray burst cools off and gets dimmer and dimmer, the light it emits shifts from high-energy gamma rays to X-rays to UV to optical light before fading away forever. The UV and optical telescope aboard Swift follows up with these low-energy observations. While it's not observing gamma rays, again, it does fascinating science throughout the entire universe. Its UV, its ultraviolet photon capabilities, are particularly valuable because there aren't many space telescopes that can observe in the range of ultraviolet light that Swift observes. So you get really unique pictures, like this image on the lower left of the Andromeda galaxy, showing regions of intense star formation activity. So just like the other telescopes, Swift UVOT has a role to play in the search for gamma ray bursts, but also contributes to the general astronomical mission of Swift as an independent observatory. Before we move on and talk about the famous discoveries of Swift, I'd like to contrast the UV optical telescope and the X-ray telescope observations of Swift. I like to joke that when you use a UV or an optical or an infrared telescope like the James Webb Space Telescope, you get beautiful pictures of the most exquisite landscapes in the universe. On the left here, you can see a nebula through the UV optical telescope of Swift. You can see stars, clouds of gas, a nearby star, and distant galaxies in the background. So it makes for a very pretty picture. When you look at a typical region of space with the X-ray telescope, though, you get a bunch of dots. If you were to zoom in on this X-ray telescope field on the right, you would be able to see individual dots representing individual photons that the X-ray telescope has observed. I like to joke that sometimes the sources, the astronomical objects we observe in X-rays, are so dim that you can name your photons. I once had an object with only 3 photons detected. I named them Curly, Larry, and Moe. But you can still do good science with those. The reason X-rays are so unique and so valuable for astronomy is because while they're 1,000 times more energetic than optical photons, for a given brightness, that means there are 1,000 times fewer X-ray photons than optical photons. So if you have an object with a totally flat spectrum in terms of energy, and you're getting 1,000 optical photons per second, it means you're typically getting about 1 X-ray photon per second in your detector. That means it's very difficult to take complex pictures of X-ray emitting objects. But despite this difficulty, X-ray photons are some of the most fascinating, in my opinion, as an X-ray astronomer, which I guess means I'm a little biased about this. They come from exotic, high-energy processes, like accretion onto supermassive black holes or the collisions of neutron stars. They probe the most extreme environments in the universe, which means despite being very rare, very difficult to focus with their gently curving mirrors, and you only get a few of them per observation, they're extremely valuable and I find extremely rewarding to investigate. So let's just summarize the design of Swift before we go into talking about its most famous discoveries. Swift uses its 3 telescopes, the burst area telescope, the X-ray telescope, and the UV optical telescope, to search for gamma ray bursts around the sky. Burst area telescope locates the burst to within about the area of the full moon on the sky, and then the X-ray telescope and the UV optical telescope follow up, find the exact location of the burst, and then watch it fade away into nothing. Because of Swift's fast reaction time, it can find the location of gamma ray bursts in only a minute or so, and then use its other telescopes to watch the burst fade away. Some scientists actually have automated alerts on their cell phone, for example, when Swift detects a particularly exciting astronomical. You can see in the timeline up here that Swift can often conduct observations within only a few minutes, observing an entire cosmic explosion as a gamma ray burst occurs. As the gamma ray burst fades away, Swift records the observations, sends them back down to Earth, and other telescopes can follow up the observations, looking at the galaxy that produced the gamma ray bursts, or looking for a remnant of the cosmic explosion that produced the high energy emission. While Swift isn't doing gamma ray bursts, though, it's doing fascinating science around the sky. So with that, let's talk about some of the most famous discoveries that Swift, a lesser known but unsung hero of a telescope, has brought to us over the past 18 years. Before we jump into that, I'd just like to point out that on this image of Swift here, you can see all 3 telescopes that are installed on the Swift Observatory. This kind of trapezoidal yellow shape here is the burst area telescope. And then on the left and right, you can see these little 2 eyeballs peeking out from this shield. Those are the X-ray and the UV optical.
Now that we've talked about how Swift works, why it's designed so uniquely, and what each of the telescopes on board the Swift Observatory contributes to its mission of observing gamma ray bursts, let's go through and talk about some of the most famous discoveries that Swift has made over the past 18 years. Obviously, this is not an exhaustive list. Swift has done amazing science for the past 18 years using its unique capabilities. But these are some of my personal favorites, the ones that I think represent the broad science that a multi-wavelength observatory like Swift can do. Obviously, like we've talked about throughout the first half of this talk, Swift is continuing to undertake its mission to detect gamma ray bursts around the sky. It's automated process of detecting a burst with the burst area telescope, and then following it up with the X-ray and UV and optical telescopes. But while Swift isn't pursuing gamma ray bursts, it's doing observations around the sky that individual scientists request and discover unique objects in their own. So let's talk about both some of the unique gamma ray bursts that Swift has discovered and some of the other discoveries that Swift has entertained. Only about a year after its launch, Swift was already detecting gamma ray bursts, and one of the first most famous gamma ray bursts detected was GRB 050904. Don't be intimidated by the big numbers in the name. That just represents the day, month, and year that the gamma ray burst occurred. Gamma ray burst 050904 was unique because it came from the extremely distant universe. Now, because light travels at a finite speed, when we use telescopes to look into the universe, we're also looking back in time. And this gamma ray burst comes from originated far enough away that it occurred when the universe was only a few 100 million years old. That is about 100th of its current age of 14 billion years. Discoveries like this gamma ray burst established Swift as a tool not only for observing the local universe, but also for the evolution of the universe over cosmological timescales, looking at the universe changing over time through detecting these gamma ray bursts, cosmic explosions across the universe. Another famous discovery that Swift made in its first few years of operation wasn't specifically a gamma ray burst, but a supernova, supernova 2008D. The name just means it happened in 2008. Swift was observing a fairly standard galaxy, looking at, coincidentally, a different supernova remnant in that galaxy. And as the animation on the upper right-hand side of this page shows, as Swift was observing this galaxy with its X-ray and UV optical telescopes, a supernova happened to go off in that galaxy itself. This is a once-in-a-lifetime coincidence to be observing a galaxy with a space telescope as a supernova happens. It's super unique because normally when we are observing supernova or other cosmic explosions, we aren't observing them with powerful telescopes as they happen. Someone notices them with a survey or another kind of broad examination, or even an amateur astronomer notices supernova first, and then more powerful telescopes follow up with it as it's dimming away. However, in this case, Swift was conducting the observations as a supernova occurred, which let Swift contribute to the valuable science of observing a supernova in real time, star exploding at the end of its life. Later that year in 2008, another famous discovery came out of Swift, another gamma ray burst this time, 080317b. Again, the name just means it happened in 2008 on March 17th. The B means it was the second supernova to occur on that day. This supernova is unique because if you were standing out on a very dark night, looking at the right part of the sky at just the right moment, you would see this gamma ray burst with your unaided eye. This is unique because this gamma ray burst comes from a galaxy 7.5 billion light years away, which means this cosmic explosion itself holds the record for the most distant object the human could see with the unaided eye. You'd just barely be able to see it, but you're looking at just the right spot, you'd see a flash of light, and then it fade away within a few minutes. This is fascinating and unique, and I feel like it connects our human experience of astronomy with cosmology and extragalactic astronomy as a whole. On most nights, when you look up in the night sky, you can only see 1, 2, or maybe 3 objects outside of our own galaxy. Normally, that's the Andromeda Galaxy and the Large and Small Magellanic Clouds, although some people claim they can see the Triangulum Galaxy with their unaided eye. However, gamma ray bursts are so powerful that you can see a cosmic explosion from 7.5 billion light years away, over, I think, 700 times more distant than the nearest galaxy to us. Sorry, just had to do some math on my head. Swift discoveries like these, again, it's discovered thousands of gamma ray bursts in its time on Earth. Another discovery that turned out not to be a gamma ray burst was Swift 1644 plus 57. These numbers look a little different from other names we've seen. This name just represents the position on the sky of the object. So it occurred at a right ascension of 16 hours and 44 minutes, and declination of 57 degrees north. This object was detected using the normal Swift transient detection protocols of Swift being alerted of a burst of high energy light and swiveling around and pointing at it. But it turns out this wasn't a gamma ray burst. After a lot of analysis, again, this happened in 2011, scientists determined that this was a supermassive black hole consuming a star. So material from a nearby star was being tidally stripped and sucked down onto a supermassive black hole by its gravitational forces. And as that material passes through the accretion disk and hits and gets near the event horizon of the black hole, the black hole system emits copious amounts of high energy radiation. This was an amazing discovery from Swift. And these sorts of tidal disruption events or interactions between stars and black holes are quite rare, showing that Swift is a powerful tool for examining them around the universe. All right, let's talk about just a couple more famous discoveries that are really weird and really far out there. The first, I'm not going to try to pronounce that name, I'll just call it Ogle 2015, was Swift helped contribute to the discovery of a brown dwarf via gravitational microlensing. And this is super unique, and we'll take a few moments to explain. A brown dwarf is an object somewhere between a star and a planet. It's massive enough to have certain types of fusion going on at its core, certain energy and efficient types of fusion of isotopes of hydrogen, but not massive enough to ignite hydrogen fusion and become a normal star. Swift discovered this substellar object in collaboration with some other observatories via gravitational microlensing. That means that the brown dwarf passed in front of a star in the background, and via Einstein's general relativity, just like the gravitational lensing we talked about in the news before this talk, the gravitational microlensing momentarily focused the light from the background star, creating a little increase in brightness all of a sudden. Swift's detection of this gravitational microlensing helped measure the mass of this brown dwarf, as well as other properties, showing that Swift not only can observe high-energy astrophysical processes like active galaxies and gamma ray bursts, but also mundane objects that aren't even producing much light themselves. Finally, the last of the fascinating discoveries I'm going to mention tonight was in 2017, when Swift contributed to finding follow-up emission from the famous neutron star gravitational wave merger. So about a few years ago, collaboration called LIGO brought online gravitational wave observatories. These are kind of like telescopes that observe not light coming from deep space electromagnetic waves, but instead gravitational waves, distortion in space-time from rapidly moving massive objects. The gravitational wave observatories had detected what appeared to be a pair of neutron stars inspiraling and colliding with one another. And Swift's observations using its UV and UVOT component discovered an ultraviolet emission from material ejected from this collision, helping establish it as a neutron star merger and conducting science not only on the gravitational wave source, but finding an electromagnetic counterpart to it. Gravitational waves is the absolute cutting edge of astrophysics research these days, and I'm excited to see where it goes over the next 10 years. But observatories like Swift will have an important role to play in following up with these gravitational waves. So these are just some of the most amazing discoveries that Swift has made. If you look on the Wikipedia page for Swift, you can learn more about these and others, big public discoveries that really have been ground-shaking astronomy. For the final part of the talk, though, I'm gonna talk about the science that I do involving Swift. And this relates Swift's multi-wavelength capabilities, its ability to observe from the optical, ultraviolet, X-ray, and high-energy X-ray light, to the science and astrophysics of active galactic nuclei. So let me talk about my research for a little bit, just to give some context about the sort of things Swift does in its downtime these days. So my mission with Swift involves chasing down gamma ray sources. Another space telescope, the Fermi Space Telescope, observes in gamma rays, that is, light even higher energy than the photons that Swift can observe. Obviously, because those photons can't get through the atmosphere, it needs to be a space observatory. The Fermi Space Telescope has observed over 6,000 gamma ray point sources on the sky. And while many of them we have good ideas about what's producing those gamma rays, over 2,000 of the sources are what we call unassociated. These means we know there are gamma rays coming from a region of space, but we have no idea what's producing them. It could be an active galactic nucleus, maybe. Maybe it's a neutron star of some type. My main project and my research focuses on using Swift to follow up at these gamma ray sources. These aren't transient sources, they're steady gamma ray sources for the most part. So using Swift's X-ray and UV and optical telescopes can follow up with these sources and hopefully find a low energy counterpart to the gamma ray emission. Here we can see why Swift is such a great instrument for doing these follow-up observations. If you look on the upper right side of the screen, you can see the typical landscape of a Fermi unassociated gamma ray source. There's just a region of space, normally a couple arc minutes on a side, so a few 60ths of a degree in the sky. And we know there's gamma rays coming from this region of space, but we don't know what it is. And if you look with an optical telescope, you can see on the left here an image from the Sloan Digital Sky Survey from that same region of space. There are dozens of possible stars or galaxies in the background that could be producing this gamma ray emission. Simply using optical telescopes to follow up Fermi gamma ray, unassociated gamma ray sources is extremely difficult because there are so many optical and infrared sources in each small region of the sky. However, using Swift's X-ray telescope, we can try and see that an object producing gamma rays might also produce X-rays. It's a fairly good bet that if something's producing gamma rays in the universe, it's probably emitting some X-rays too. On this page, I've given some examples of some of the objects that produce a lot of the Fermi gamma ray sources and therefore may also be producing the Fermi unassociated sources. These include active galactic nuclei, which is a supermassive black hole with an accretion disk of material falling down onto it. It might include a pulsar, which is a neutron star, a husk of a massive star spinning rapidly. Or it's an X-ray binary, where a neutron star or a small black hole is accreting matter from a nearby star. Again, all three of these processes produce copious gamma rays. So large amounts of gamma rays are emitted through these processes, as well as X-rays. So if the objects producing the unassociated, the unknown Fermi gamma ray sources are producing X-rays, we might be able to follow them up with Swift, because Swift can observe an X-rays and then UV and optical telescopes. So my project focuses on using Swift's X-ray telescope to look at the regions of Fermi unassociated sources. On the left side of the page here, you can see a Fermi unassociated source in the blue and red circles. You can dimly see there. And then using Swift X-ray observations, we found a variety of X-ray sources in the same region of space. And you can see the source labeled 3 is in fact sitting right in the middle of the Fermi unassociated source. Using various analysis techniques, we assume that this X-ray source in the middle of the gamma ray region is a lower energy counterpart to the unknown gamma ray source. And now that we have its location to within 5 arc seconds, we can go back to UV, optical, infrared, and radio catalogs and see what else is at exactly that spot on the sky. After collecting the information of that counterpart, my research uses a machine learning technique called a neural network to try and classify each gamma ray source. Is it a pulsar, an active galactic nucleus maybe, or something else entirely? That's what my research is focusing on right now. On the right side of the screen here, you can see a realization of what the output of one of those neural networks looks like. So using Swift's multi-wavelength capabilities, we can chase down these gamma ray sources, locate them with great precision, and then build a multi-wavelength spectrum of each. Because Swift can observe in such a wide range of the electromagnetic spectrum, from the optical to the ultraviolet, X-rays, and high-energy X-rays, we can build a spectrum of the object. Think of a spectrum, a multi-wavelength spectrum, as like a rainbow, red through purple, except extending all the way from the lowest energy light, radio waves, all the way up to gamma rays. On the right side of the picture here, you can see how a spectrum for one of the Fermi unassociated sources includes radio light, infrared light, UV and optical light from Swift, X-ray observations from Swift, and then gamma ray fluxes from the original Fermi observations. Swift is foundational in building these spectra and investigating what can be producing these unknown, mysterious gamma ray emissions. One other advantage of Swift is that it's operated right from State College, Pennsylvania. There's a mission operations center where engineers and scientists keep the telescopes working, scheduling observations, and that makes it extremely easy to go from Davy Laboratory, right on the Penn State campus, to the Swift Mission Center. It enables collaboration, troubleshooting is extremely easy, and I've several times requested observations on Swift, and with the help of the engineers and scientists at the Operations Center, made those observations happen in as little as a month. So Swift is not only a powerful multi-wavelength observatory, but also a very accessible way to do science, especially for folks working at Penn State. Overall, again, Swift is a unique but slightly lesser known telescope. Its multi-wavelength capabilities let it observe a huge range of the electromagnetic spectrum, and its rapid response times have made it, over the past 18 years, the perfect tool for examining gamma ray bursts and other explosive cosmic phenomena around the universe. I hope in this talk you've gained a little appreciation for this unsung hero of high energy astronomy, and have plenty of interesting questions about what's happening next for this plucky little space telescope. With that, I'm ready for your questions. I'd like to thank, of course, my advisor, Abe, and everyone else in the high energy research and instrumentation groups at Penn State, who you can see on the picture on the right. All right, I'm happy to field any questions now. Alternatively, you're welcome to email me after the fact. My email's right here if you like. So thank you very much.
That somebody said there, you got a great comment on the YouTube from somebody saying Steve is an amazing teacher. His students will be lucky to have him. So you got wonderful compliments from our YouTube audience already.
I appreciate it. Thank you.
All right. So one of the things I wanted to clarify with people is, right, so the Neil Gehrels Swift Observatory, original intention was to study gamma ray bursts, but it doesn't actually observe gamma rays. We're detecting gamma rays, but a gamma ray bursts, but we're not looking at gamma rays. We're looking just at the high energy X-rays. How far above these high energy X-rays are the actual where's the boundary line on that? Can you explain that a little bit?
So of course, thanks. That's a very good question. I'll talk first about kind of the division between gamma ray and X-ray astronomy. And then about why Swift observes X-rays specifically in its mission to pursue these gamma ray bursts, not the gamma rays themselves. So the electromagnetic spectrum, again, extends smoothly from radio waves all the way up to gamma rays and even what astronomers call very high energy photons. These are photons with even higher energies. Generally, the division between an X-ray and a gamma ray, while it's a little bit arbitrary, it's about a million times more energetic than the photons that we humans see. So mega electron volt, which means a million electron volts, a million times more energetic than a photon, is kind of an arbitrary boundary, but around there is the division between X-rays and gamma rays. The Fermi Space Telescope.
One second. So you're saying that you said that the X-ray telescope goes up to 150 keV, right?
150 kilo electron.
An MeV would be about roughly six times more energetic than that.
About six times more energetic, yeah.
Right.
So I mentioned briefly in the talk the Fermi Space Telescope. The Fermi Space Telescope specifically observes gamma rays, and it goes all the way up to hundreds of billions of electron volts. That is 10,000, 100,000 times more energetic than the X-rays that Swift observes. Sorry, just had to do some quick math. So if Swift is observing gamma ray bursts, so second part of the question, why is it built as in two X-ray telescopes and a UV optical? That's because the gamma rays are the very first photons that emerge from a gamma ray burst, but Swift can't swivel instantaneously to point at the gamma ray. By the time Swift arrives at the location of the gamma ray burst, the burst is already starting to fade away, kind of tailing off, not only growing fainter, but also cooling down to lower energies. So, like I said, as the gamma ray burst cools down, it goes from gamma rays to X-rays to UV photons to optical. And by the time Swift is conducting its observations, it's looking for the gamma ray burst in the X-rays to see this transient appear. The Fermi Space Telescope does occasionally detect gamma ray bursts itself, but Swift is specifically designed to do so, using its unique capability.
Okay. And this, of course, also contrasts to the Compton Gamma Ray Explorer. That was one of the great observatories in the 90s and the 2000s.
It's true. Yeah, I sometimes use Compton, that archival data from that observatory, which was still a pioneering observatory for studying gamma ray.
Great. All right, Grant, why don't you turn on your video and let's chat on that. There have been some questions in the chat. I took some notes on it there, but what question from the chat did you choose to highlight?
I like this one. So Swift obviously has had a a tough life so far. Was there a predecessor to Swift, and is there a planned successor to Swift? Because a lot of people have never heard of this.
Sure. So Swift, as a multi-wavelength observatory that can react with such rapidity to gamma ray bursts, that's a really unique combination of qualities. In the past, there have been multi-wavelength X-ray observatories. There have been UV and optical telescopes as well. But Swift kind of is really a pioneering telescope for combining all of these detectors together, all of these capabilities together into a single instrument. That unique capability is why I really hope Swift gets decades and decades more in its life, continues to do these observations, because it combines X-ray, ultraviolet, and optical observation. Successors to Swift, recently the astronomy community put together and released the Decadal Report, which presented kind of the next 10 or 15 years of goals for the astronomy community. And while one of the main proposals in the Decadal Report was a flagship telescope, a telescope just as big as the Roman Space Telescope or James JWST, it also proposed a more medium-sized X-ray observatory. That might complement Swift's capabilities, but I don't think there's an explicit plan for such rapid response and multi-wavelength capabilities that Swift does, which again is why I hope it survives for a long time.
Okay, so that begs the question, how long do we expect it to survive? What's going to be the problem? I mean, you said you had a reaction wheel problem. Is that going to plague you, or is that, you deal with that? What's the lifetime? What's projections for lifetime? I know you can't give me a lifetime.
I use Swift for my science. I would defer this question to the fantastic engineers who work actually just down the road from where I work, and managed to get a solution to the problems with Swift and keep it going even though a reaction wheel had a problem. Swift is operated right out of State College, the town where Penn State is, which means it's very easy to collaborate, to contact the engineers who make it work automatically. I like to say that, as an astronomer, I use the observations that Swift takes, but it's the engineers who really make it happen. So I'm indebted to them not only for putting Swift up in space, but also for making sure it's still working in 18 years, and I hope for decades in the future. What might eventually take it out? Most likely, funding cuts. But who knows?
That one.
Yeah.
They're much more devious than the micrometeorites.
Yeah. At least micrometeorites are stochastic, random.
Yeah, exactly. All right. So that brings us a question that somebody had, a nice question. You said you had a reaction wheel problem, right? Does that affect the slew rate? Because you said you can go anywhere on the sky in 90 seconds. But that's having 6 reaction wheels. What with the problem? Does that affect it?
I don't know the details, not an engineer on this, but I presume it would slightly impact the slew rate. This is just a presumption on my part. The reaction wheels, again, think of them like rapidly spinning gyroscopes. And by slowing them down or speeding them up by conservation of momentum, the entire telescope can turn around. So if one of those reaction wheels is taken out of commission, it might be more difficult for the telescope to turn in a certain direction with as much speed as it used. But because Swift has other reaction wheels kind of taking up the slack, it can still slew around with great rapidity.
Okay, and I will just note that Hubble has reaction wheels as well. All your space telescopes need reaction wheels to I don't know if they need them, but I mean, Hubble uses them, so it's the same type of thing. But Hubbles are meant to go really, really slowly, not be as fast as Swift.
One thing I do know from my conversations with people who build space telescopes and observatories is that often the most common part of a space telescope that might fail when it's already up in space are the moving pieces. If I remember when James Webb Space Telescope was deploying, everyone was holding their breath as each intricate step happened. And now that it's fully deployed, it can happily sit up in its fully deployed state. With Swift, these reaction wheels are spinning around with great rapidity, and that means they've been spinning continually for the past 18 years. And obviously that'll put some wear and tear on a telescope. As for alternatives, you could use little rocket engines like altitude control thrusters, but you would run out of propellant for those eventually. I would love to see a gamma ray or an X-ray observatory on, for example, the far side of the moon, because you could use the ground to aim the telescope and you wouldn't have to worry about reaction wheels. But that might be a little pie in the sky or pie on the moon for the time being.
Okay, moon pies.
Delicious.
All right, Grant, what did you find? What other questions have you found?
So I like this one. Some of the context that people have for a telescope like this is... Oh, go ahead.
No, that was just an echo of you.
Oh, okay. So one of the points that people have as a comparison would be something like Chandra. What are the differences? I mean, obviously they're intended for a different purpose, but how would you compare and contrast what Chandra does versus what Swift does, and how the science is done with both?
Sure. So I've used data from Chandra and a European telescope named XMM Newton. Those are both X-ray telescopes that have been up for about a similar length of time as Swift, maybe 10, 15, 20 years maybe. Chandra and XMM Newton are both specifically X-ray telescopes. They are tuned and optimized for observing in the X-ray. Kind of the same range of low energy X-rays that the Swift X-ray telescope observes. So between, Swift XRT observes between 0.3 and 10 kiloelectron volts, so 1,000 times more energetic than what our eye. Because they're tuned specifically to do X-ray astronomy, Chandra and XMM Newton they're significantly larger than Swift. There was much more investment into them. We're hoping they will last a long time as well. And by focusing on X-ray astronomy, they can do very high-resolution spectroscopy. That means spreading out X-rays into a rainbow to detect little emission lines or particular atoms. Swift can do this too, but because Chandra and its European counterpart XMM Newton are specifically aimed to do X-ray astronomy of that type, they can do it with a little stronger capabilities than Swift can. But again, all these space telescopes are complementary. Swift will sometimes detect a gamma ray burst, and Chandra and XMM will think it's interesting enough and follow it up over there. Swift can follow up discoveries from those, but slightly fewer photons detected. So complementary, but Chandra and XMM Newton focus specifically into X-rays with a little more devotion.
Absolutely. So are FGRB, so gamma ray bursts, are they still being detected? And do we know where they are coming from?
So the question says FGRBs?
It says FGRB, yes.
Okay, that might be referring to a fast gamma ray burst.
Okay.
Over the past few decades, especially with Swift observations, kind of characterize gamma ray bursts into two types, fast and slow, kind of just based on how rapidly they show up and then vanish. The one time where astronomers get the name is very clear what it actually means. So over the past 20 years, Swift especially, but other telescopes as well, have really contributed to our understanding of gamma ray bursts. Obviously, with such explosive cosmic events, it has to be some cataclysmic change in the universe. Things we think can produce gamma ray bursts include supernova or the star collapsing, for example, the formation of a neutron star, maybe, wide variety of other energetic processes. Swift continues to observe these. Again, astronomers sometimes they sign up for a text message service whenever Swift turns to a new gamma ray burst, for example. And all the gamma ray bursts that Swift observes are available on a public repository as well. So it's a fascinating way to get students involved in science using this public data of gamma ray bursts to try and learn about the universe. But yeah, Swift has been instrumental in helping our understanding of gamma ray bursts as energetic explosions of stars involving compact objects like black holes or neutron stars emitting this high energy radiation from energized particles.
Right, and that story of the gamma ray burst has grown up over several generations of space telescopes and such, going back to the original ones. Just looking at the isotropy of gamma ray bursts around the sky, getting that, and being able to tell that they weren't coming from our galaxy, that they were coming extragalactic, which was quite the step change. Maybe you're a little young to have experienced that step change, but the step change.
That's something I forgot to mention in my talk. Yes, that the gamma ray bursts come evenly distributed across the entire sky, which means they come from distant galaxies. If they were just along the plane of our own galaxy, which cuts a stripe through the sky, we would infer they're coming from our own Milky Way galaxy. But they come from the entire sky. I bet sorry, what were you saying?
Oh, I was just saying that that was the expectation. When they did those first studies, we were expecting to see, along the plane of the galaxy and then a little bit extra, but no, it did not come out that way. And that was impressive, because that meant the energies of these gamma ray bursts just got a couple of magnitudes larger.
With being so far away that they were so bright in gamma rays, yeah, they clearly emitting galaxies worth of energy in just a few seconds is a truly mind-blowing scale.
All right, Grant, we have other questions from the chat.
Yes,
I see the chat moving, but I can't read it while I'm looking at both screens here.
You're all good. There was another one that actually kind of piggybacks off of another one. You were saying that the data is freely available and is a good way to engage students. What kind of things are being done with Swift to engage astronomy students and other people to raise awareness and start having this data being more publicly known?
That's a really good question. There's a website that NASA maintains called HIASARC, which is an archive of a wide variety of raw data from high energy telescopes and other telescopes as well. I use data from HIASARC.
Shamelessly plug
every day. It's a fantastic resource. I download my data from there, except if I've done a specific observation at a specific object, I download a little more. HIASARC is a great archive. For HIASARC and other archives like it, it helps to have a little bit of astronomy expertise in analyzing the data, because you're really just getting raw photons. Remember, X-rays, we can really count and name each and every one of our photons. So the data you download is sometimes just, here's a photon, energy, location. Photon, energy, location. There are other ways to access the data products, though. Swift has an automatic analysis program that produces spectra and time curves, so how bright an object is over time. That's a great way to get students involved in high energy astronomy. Those are available on the Swift website. They're really easy to use. You can just type in an object and Swift can produce these science products for you. So Swift especially is a really great telescope for that. And I'm going to make one more plug for Swift. Swift has a target of opportunity form on it, which is when astronomers or scientists think that Swift will be a useful or valuable telescope, you can submit a target of opportunity request asking for observations on Swift, and you can get those observations scheduled, observed, and returned to you in as little as a month or something. It's a very streamlined process. That's because Swift has, it's constantly observing for gamma ray bursts, but like most telescopes, it has free time, and it takes those requests. One thing to take note if you're a scientist listening and thinking of using the target of opportunity request, there's an importance scale that you select. Most, like if an object is a steady state object, it's going to be there tomorrow or the next million years, you can put an importance of 1 or something. But an importance of 5, that sends out a message to the Swift operators and wakes them up in the middle of the night. Like, this object's going away, quick, you need to point at it. So don't do that unless you really mean it.
I will answer a bit of that question myself, because in trying to get to students, there's a lot of preliminaries you need to understand the Swift results, right? You have to understand the electromagnetic spectrum. And generally, students don't get that until high school level in terms of understanding what X-rays are, ultraviolet, and the different wavelengths of the electromagnetic spectrum. So high energy astronomy is sort of hampered in that it's not part of the typical science curriculum until you get to later points. You can't do middle school X-ray science, unfortunately, because the middle schoolers won't have X-rays in their toolkit to understand this stuff. But when you can get to the the high school, the upper level high school things where they can, this is fascinating science, because you get the implication as we were talking about that you're seeing gamma rays and they're coming from the other side of the universe, and so that the implications of the energies is a straightforward understanding that I think would work really well in a classroom setting. All right, other questions?
What kind of an orbit do we have with Swift? Is it similar to what we have with the other space telescopes? And what kind of interference do you have in your observations?
Sure, really good question. And I'll contrast it with the James Webb Space Telescope and the Hubble Space Telescope, which people here are probably much more familiar with. So as you all saw in the exciting launch video earlier this year, the James Webb Space Telescope is all the way out beyond the orbit of the moon at the L2 point. L2, yeah. So this is far, far beyond low Earth orbit. Low Earth orbit is only a few hundred kilometers up from the Earth's surface. Many people think the space station, the space shuttle, these telescopes orbit very far away. They go out and visit other planets. No, it turns out that Swift passes overhead much closer than probably the nearest big city to me right now. It's probably closer from me to Swift than it is from me to the Space Telescope Science Institute, for example. Swift only orbits a few hundred kilometers above the Earth's atmosphere, much like the Hubble Space Telescope. And that means every few orbits or every day or something, it'll pass through the South Atlantic Anomaly, which is the most mysterious and cool-sounding thing we have in high-energy astronomy.
That sounds like the Bermuda Triangle of space.
Yeah, it does. It kind of is. It's a defect, kind of a warp in the Earth's magnetic field that makes high-energy particles pass through this region of space with more regularity. And because Swift is a high-energy space telescope, whenever it passes through this anomaly, we have to be extra careful not to have our observations degraded or the instruments damaged as well. So because Swift is just above the Earth's atmosphere, it does have these interferences from the Earth's local region of space.
And I will say that, yes, the Hubble passes through the South American anomaly, and it has to be, data taking there has to be calibrated, especially, or even not taken. Especially early on in the Hubble mission, the SAA was a significant factor in determining your observations. All right, other questions, Grant? It's about time for the last question. No more questions.
Time for the last question.
That was the last question. All right.
That was the last question.
Well, thank you, Steve, for this partial talk that you've given. We will set it